Hey guys, Mr. Lewis here. I want to talk to you today about the next kind of subject in our discussion of solutions. And really that's what I want to talk to you about intermolecular forces. These are those forces that cause molecules to stick together. So why? Why do molecules stick together? Why does water or liquid at room temperature while why does it then become a gas? When you heat it up? Why does it become a solid as you cool it down? Um, so we're going to talk about what those forces are that hold things together. So let's get into it. So as we start, we want to talk about the difference between an intermolecular force and an intramolecular force. So first, intramolecular forces are defined as those interactions within a molecule. So if we're talking about, I'll say water, H2O, that's those interactions between the hydrogens and oxygens within the molecule. So for chemistry, when we're talking about these intramolecular forces, typically we are talking about ionic and covalent bonds, those bonds between the atoms within a molecule. So again, focus on a molecule, those within that molecule. There's another one, hydrogen bond can actually form a intramolecular force within a molecule. If you think back to your biology, proteins start forming their complex structures and are held together by hydrogen bonds within that molecule. So it's all the same molecule, and those hydrogen bonds are holding that into a certain place. So we call those intramolecular hydrogen bonds. But for what we're talking about for our class, we're going to be saying those are really more ionic and covalent bonds. So intermolecular forces then are those forces between different molecules. So we're not talking about the hydrogen oxygen of a water molecule. We're talking about hydrogen interacting with the oxygen of another water molecule. So these forces can be either attractive or repulsive, and we'll get into most of that is all due to charge. So when we think about the strength of intermolecular forces and how that affects the state of matter. So stronger intermolecular forces result in increased melting and boiling points. So if we look at our, I want to pull up a little laser pointer here. So if we are looking at this here, we are looking at a solid, liquid, and gas. So if these are all at the same room temperature, or same temperature, the intermolecular forces in this solid must be much higher than those in the liquid or those in the gas. And as you can see, we have increased kinetic energy within those molecules. So something that has a low intermolecular force at the same temperature, these molecules are going to be bouncing all over the place because they've broken away from the other ones. The forces holding them together are weak. So a really high, something that's got a high intermolecular force is going to need a higher temperature to break those intermolecular bonds, to get those molecules to fly away from each other. So now let's talk about the types of intermolecular forces. So the first one we're going to talk about is dispersion forces. Dispersion forces are those forces that are caused by interactions between electrons. We get into the next one is dipole-dipole interactions. These are between positive and negative charges within a molecule. And finally, we're going to talk about hydrogen bonding, which is the strongest of the intermolecular forces that we're going to discuss. There is one that's a little stronger, but we're going to skip that one for now. So to understand especially when we get into dipole-dipole and hydrogen bonding, we need to talk about bond polarity. So bond polarity is all about sharing of electrons. Is our covalent bonds sharing the electrons equally or not equally? So if you remember back from our unit on chemical bonding, we had the difference between ionic and covalent. And typically I said ionic is where you steal one atom steals the electrons of another. And that's because the one that is accepting, taking the electrons away from the other, has a really high electronegativity. And then when you talk about sharing electrons in covalent bonds, where the electrons are being shared between the two, well, that can actually be an equal or unequal sharing. And that all depends on electronegativity. So when we talk about nonpolar electrons, back to my pointer here, Non-polar covalent bonds, our electrons are being shared equally. Oops, sorry. So an example would be methane, CH4. Electronegativity of hydrogen is 2.2. There's no units right there for now. Worry about. And carbon is 2.5. With electronegativity, we are dealing with, in this case, we're looking at a difference about 0.3. And we can tell whether a covalent bond is, or a bond is nonpolar, nonpolar covalent, polar covalent, or ionic based on the difference between the electronegativities within the atoms that are forming that bond. So in this case, we're looking at 2.2 and 2.55, a difference of 0.3. Anything less than a difference of 0.4 is considered nonpolar. They're shared pretty equally. So the electrons are spending an equal amount of time circling both atoms. When we get anything over 0.4 to about 1.7, we're talking polar covalent bonding. So that's where our bonds are being shared unequally. They're spending more time around the atom that has a higher electronegativity. So again, we're talking about a large difference in electronegativities and unequal sharing. So let's look at an example of HCl. Again, our hydrogen has an electronegativity of 2.2. Chlorine has an electronegativity of 3.16. That difference is greater than 0.4, but less than 1.7. So we're talking about a polar covalent bond. The electrons of hydrogen are spending more time around the electrons of around the nucleus of chlorine than they are around hydrogen. So when this happens, one side of the molecule becomes positive and the other becomes negative. The whole molecule itself has a neutral charge, but there's kind of a partial positive and a partial negative charge. So then when we talk about those, we're looking at opposite charges, we're getting into that whole idea of opposites attract. So the positive side of one molecule will be attracted to the negative side of another. So we can see these examples of not only HCl, but water and ammonia will form our polar covalent, are forming polar covalent bonds. There's a lot of different molecules that are like this. All right, so now let's talk about those forces. Again, first one we're going to talk about is our weak one, dispersion forces. So dispersion forces are really caused by moving electrons causing a temporary charge around the molecule. So as we get electrons circling around a molecule, it's a random where they're going to distribute themselves. And so occasionally you're going to have a larger density around one side than the other, causing a very, very, very temporary partial charge. So also on one side of the atom is going to be, one side of that molecule is going to be positive, the other side is going to be negative, allowing for attraction between other molecules that are doing the same thing. And so it's also the same time as like molecules come close to each other, those electron clouds are going to repel each other, causing that same temporary change in density away from each other, causing, again, positive and negative charges. One side, again, becomes positive, the other negative, allowing for a very, very temporary attractive force. And larger, heavier molecules tend to have stronger dispersion forces than smaller ones because there's a larger cloud around it. So you can get a larger change in density of the electron cloud towards one side, causing a much bigger charge. So it becomes a stronger force. When the stronger force, because that typically, even though you have a set of nonpolar molecules, a very large nonpolar molecule will have a much higher melting and boiling point than something that's really small. So we look here. Here's a visualization of it. These dispersion forces are also sometimes called London dispersion forces, named after the chemist Fritz London. So you can see as these electrons moving around can cause, as more electrons move towards one side of an atom, they can cause a temporary dipole there, which then can induce a dipole, repel the electrons from into another atom, induce this dipole, and create this temporary short-lived attraction. This doesn't, we're talking, you know, milliseconds where this happens, but they induce that opposite force in the neighboring molecules, which then cause these weak momentary attractions. And these are the weakest forces, the intermolecular forces that we're going to discuss. So think about that one molecule has the electrons all of a sudden become more dense on, say, this side, which induces a temporary dipole in another molecule by repelling those electrons over to here, making this side more dense, more negative. So then we get this attractive force here, allowing for a weak, short-lived attraction. All of a sudden, these electrons then will kind of redistribute back to more neutral, balanced, and then the same thing will happen here until, again, another molecule does the same thing, causing another temporary dipole, and then inducing dipoles in others. All right, dipole-dipole interactions. These are interactions where we have, instead of a nonpolar, we have a polar molecule. Where they have polar molecules are those that have a permanent polarity on one side, and the other one has a permanent dipole. The stronger that dipole, the stronger the charge. The stronger the charge, the stronger the attraction to other molecules that have charges. So when we're talking about dipole-dipole interactions, we're talking about an attractive force between molecules that have permanent dipoles. So here we're looking at HCl. So as I said before, hydrogen has a very low electronegativity, chlorine has a very high electronegativity. So the electron, while being shared, is being shared unequally, and chlorine is spending the electrons that are more dense around chlorine than they are around the hydrogen. So if we're looking at another HCl molecule, the positive charge on the hydrogen is going to be attracted to the positive charge on the chlorine. And this is a decently charged attractive force. It's obviously stronger than those London dispersion forces. It's not as strong as something like an ion dipole, where you would have something like this with a dipole and then an ion over here instead of another dipole, another molecule like this. Say instead I had just sodium or something like that, it would be much more strongly attracted. So as you can see down here, when we get into, sorry about that, we get into more of into solids, you can see they form this nice lattice work where you have the positives and negatives lining up opposite each other, and positive and negatives, and they can form a very strong attractive force that holds them into place much more strongly. Again, increasing the melting points, increasing the boiling points of this material. All right, next one is our hydrogen bonds. So hydrogen bonds are specific because we were talking about hydrogen and bonds being used as part of that interactive force, or intermolecular force. So as an attractive force exists between the covalently bonded hydrogen atom of one molecule and a lone pair of electrons or electronegative atoms of another molecule. So this is a very polar molecule, hydrogen with fluorine. So we have a 2.2 versus 3.9, 3.8. So it's a really large charge difference, or electronegativity difference. So again, really strong charge over here because we have a lot more electrons over here than we are going to have around the hydrogen. And what this does is kind of expose the hydrogen nucleus, and we'll get in that next slide. So the hydrogen then is, to form a hydrogen bond, you must have a hydrogen that is attached to an electronegative atom. Typically, we're talking fluorine, oxygen, or nitrogen. And the higher the electronegativity of the bonded atom, so higher electronegativity of this one, the stronger that hydrogen bond is going to be. So Hydrogen bonds are stronger than other dipole interactions because hydrogen does not have an inner shell of electrons. Remember, hydrogen has one electron or surrounding a proton. So that electron, if it's being pulled away from the nucleus of the hydrogen, you're exposing that nucleus, and that creates a high positive charge density around the hydrogen. So we're talking about a very strong positive charge versus if we were looking at something that does not have, we're talking about, say, the difference between carbon and chlorine. Carbon has a bunch of electrons on the inner shell, that as well, two, I shouldn't say a bunch. There's two electrons in the inner shell. Once you've kind of pulled the valence electrons away to be shared with something like fluorine or chlorine, you're still not completely exposing the nucleus. Where with hydrogen, you're essentially exposing that nucleus and you're creating a high positive charge density. Where with carbon, you're pulling away a valence electron, you still have two more electrons in there shielding that positive charge. So the exposed nucleus is attracted to a nearby electron cloud, especially those of the lone pair electron, unshared pair of electrons on electronegative atoms. So if we're looking here at hydrogen and fluorine, this HF, we have our exposed hydrogens going to be attracted to this pair of unshared electrons on fluorine, or it could be attracted to this one or this one. But we are having this strong, again, we're not sharing electrons, but it's a strong positive and a strong negative charge pulling them together, so creating a really strong, a fairly strong bond. Not as strong as ionic bonds or as strong as covalent, but still relatively strong compared to other intermolecular forces. So how does hydrogen bonding affect some of the properties that we're going to be talking about? So let's think about boiling point, and why would water have a higher boiling point than hydrogen fluoride, or ammonia? So let's think about that. We got a very strong hydrogen bonds in all of these. So we can form hydrogen bonds. We have fluorine, very negative, our most electronegative atom. So now we're going to obviously have hydrogen bonding there. We have oxygen, again, a highly electronegative atom. So we're getting a dipole, but this, because it's hydrogen, a very strong hydrogen bond. And the same again with our ammonia. But how can we tell the difference between these? We think about first, let's look at oxygen, let's look at water. Water has two hydrogens that can form two hydrogen bonds. So while the oxygen is not as electronegative as fluorine, pretty close, but not quite, the hydrogen bond we have there, so the hydrogen bonds individually are slightly weaker than the hydrogen bonds formed in HF, but we can form two hydrogen bonds. So those two hydrogen bonds are going to be double the strength of just a single one. And so we have an overall higher strength of the hydrogen bonds within water, causing a much higher boiling point, taking much more energy. We've talked about much more energy to break those bonds, to get them to those intermolecular forces to get broken and melt or boil the water. So now if we compare our HF to our ammonia, fluorine's much more electronegative than nitrogen. So we have a stronger bond between the HF and the nitrogens. And you may say, oh, well, I have three bonds here, but in reality, we're going to have the nitrogen only has one single lone pair, where again, oxygen has two lone pairs. So really, we can only form each one of these can only form one bond, one hydrogen bond. And same with hydrogen, HF can only form one hydrogen bond. So while we do have three hydrogens, again, we only have one unshared electron in our ammonia. Same with this hydrogen HF, we have formed one hydrogen bond there. So because fluorine is more electronegative, it's going to have a stronger single hydrogen bond than the ammonia. So that's why water now has a higher boiling point than hydrofluoride or ammonia. I hope this kind of explains some stuff. Please make sure you have filled out the worksheet that goes along with this as you go. This is also going to be posted in Schoology so as a standalone slide deck, so you can go through and kind of review anytime you want. Hope this helped, and we will talk more later. Thanks so much. Bye.